Good morning, good afternoon, good evening to all of our attendees here for this week's Geek Speak. We want to extend a warm welcome to everybody. We look forward to spending the next hour with you. My name is Matt Burns, Technical Marketing Manager here at Samtech. And as always, I am joined by my esteemed colleague, Scott McMurrow. Scott, how goes it today?
It's great, Matt. How about yourself?
Hanging in there. Looking forward to a good technical presentation from one of our favorite folks at Samtech. Can you give us a brief intro on who our presenter is today?
Yeah, today we have Rich Mellitz, distinguished engineer and all-around really good guy. And Rich was the developer of the ERL, Effective Return Loss Methodology, for the IEEE, and it's being adopted by IEEE and other standard bodies. He's going to give us a very, very good presentation on what exactly is effective return loss, how is it computed, what are some of the caveats about it, and that sort of thing. And I'll remind everybody that in 2 weeks, the next presentation, which will be part 2, which is how to use it for launch design and things like that. So we can kind of tie the 2 domains up. So first you need to learn about it, and then you can learn how to type them into the Q&A at the bottom. Please don't use chat. I'll pay attention to it. And we'll try to answer them along the way. There are a lot of slides here. So Rich is going to be going very quickly, and I've already taken up some of his time, so I'm going to turn it over to Rich now.
Good evening, good afternoon, good night, whatever. Anyhow, this is Rich Mellitz, and I am going to talk to you a little bit about effective return loss. Just to let you know, I believe Matt is going to be turning the slides for me. If I lose internet, which is entirely likely at some point, it comes back in about 2 to 3 minutes. So please be aware. Anyhow, moving forward. Next slide. What are we going to talk about? We're going to talk about a little bit of what is ERL, some return loss and performance issues. First example is a little bit about TDR, pulse TDR, how do we compute ERL, and discussion of the parameters and how do you use them in the COM tool. And advanced topics would be package loss and DFE augmentations. Anyhow, and then we'll finish it up with a summary. Next slide. This is it. If you get nothing out of it, this is it. ERL takes the left-hand curve, which is a bunch of squiggles, and turns it into a number, a dB number on the right-hand side. It's a scalar. Okay, it's computed from the self-port parameters, the return loss parameters versus frequency. It's statistically it's a statistically reduced value that what you would see statistically for digital signals at a particular test point, which is that port. It measures both compensable and uncompensable ISI. Moving forward, next slide. Okay, return it. It's, you know, what was return loss? Return loss is just measurement of reflections. And ERL is hypersensitive to this. It's very, very sensitive to it. So the good news and the bad news. The good news, it's very sensitive. The bad news is you got to figure out what to do with all the sensitivity. So it's sort of like bumps on a road, and that's really what reflections tend to look like. I mean, but it's not exactly that. Moving forward. So what we really have here is a transmission path from A to B, and we're going to use 3 boards in an example here. We're 1 board, 2 board, 3 with some sort of separable interface in between. Guess what? Between A and B, we already have the bumps included. So let's look at board 3 as an interchangeable part, and we'll talk about return loss. Next page. So the really only question we have is really how much more reflection can board 3 have and still get successful transmission between A and B. So the challenge is to quantify it in a meaningful way. Moving forward, next slide. Well, it sort of matters if you have what we're talking about. Like if we talk about this road, the results are somewhat different between a Hummer and a Ferrari. And it's much more closely related to is if my Hummer is towing a trailer. Well, bumps I see at the trail or a train, it's like I get a bump, but how does that affect do I derail the train 20 cars back? So it's sort of like interactions of reflections. And so therefore context matters. So how do these reflections behave for a data stream? And of course, reducing reflections is always good for performance. May cost you. It's good. Next. Historically, we use masks to get a handle on on return loss. And although it's very easy to tell when you have very, very good return loss, it's also hard to say what passes and what fails. You can argue about it easily, but we're going to go through an example here to show you the issue. And setting these limits can be really a challenge. There doesn't be a clear way to do it. You could rationalize it. You could argue about the rationalization, but there's still no good way of doing it. Let's use an example to illustrate. Next slide. So this mess of a collection of transmission lines, you can call this a channel from A to B, is basically made up of like 3 boards, just like I showed before. Some transmission lines, some capacitors to represent vias. You can see what I have here. We're going to do something very, very similar. Now we are going to focus on a board 3, and board 1 is similar to transmitter and receiver boards, maybe packages, and board 2 is similar to low loss cabling. And this has been designed to sort of suggest that it's fairly low enough loss so that most of the reflections we're seeing have to do with are mostly the impairments in the channel. So we can look at reflections much more clearly if we don't have crosstalk and we don't have noise. So next slide. So we're going to use this example, 100 gigabits per second PAM4 signaling at 53.126. I guess that's wrong. It should be 325 gigabaud. Anyhow, there's going to evaluate board 3 for 3 variations: PCB1, PCB2, PCB3. In all cases, the loss end to end, die to die, is about 12.5 dB at 26.6 gigahertz. No jitter, no noise, and in order to get this really to work with any kind of loss, you sort of have to sweep the transmitter precursor and a receiver CTLE. So we're just going to do that, and we're going to look at the channel operating margin for all 3 of these moving forward. Remember, I had board 1, board 2, board 3, and now I'm going to have PCB1, PCB2, PCB3. So channel operating margin can assign a quality at some minimum error detector ratio, bit error ratio. We're going to use that to compare the designs. And if you look at these, what you can see is that the red curve is clearly, looks from a return loss perspective. Remember, all the losses are about the same, the insertion loss. A little bit better, maybe 2 might be a little bit worse and 3 looks like, quite a bit worse. Moving, and again, this is return loss, dB versus minus, it's dB versus basically frequency. And next slide. So what's the verdict? Well, 1 and 2 kind of are about the same. 1 is a little teeny bit better, and 2 is just a little bit better. 4.3 dB versus 4.4. A tenth of the bit error ratio just for that channel is probably 2.1 e to the 6. The other one is 2.6 e to the 6. The one on the right, which is which comes in a far third, and these are the parameters that are used. And I think I got that in another slide. What PCB1, what those parameters mean in terms of C1, C2, and R1 in length. But and this is no big surprise. So next slide. Okay, just when you think you've got it all figured out, let's modify PCB a little. We've changed some parameters in here, and you can review these values at your leisure. But PCB3 performance, which I'm calling PCB modified in the graph on the right, actually improves. The old COM was 2.3, as we showed before, and the modified COM now was 3.3. So, the return loss kind of looks worse for PCB3. It doesn't look like, or the higher frequencies, not much change. And we get a lot better COM. That's interesting. And we don't have this, haven't really showed you how to do this, but the ERL gets better on PCB3. It's hard to gain insight from just the plot. So historically, when you get performance issues, you usually go to a TDR. And it sort of gives you a hint about what's going on. Moving to the next slide, this is how TDR is done. It's basically a unity step, and we go through a series termination resistor to a test point, measure with the sample head at a test point, and we compute impedance at that point. So we normally look at it's a voltage of time curve that's converted into impedance versus time. Is it characteristic impedance? No. Is it real impedance? Sort of. Let's move to the next slide. What happens if we change that source this time? Remember we talked about setting data into a pulse. So the difference this time is same setup as before, but this time I send a pulse down through, like what might represent a single symbol going through a channel, and again the series resistors, and I end up with what I'm calling a pulse TDR signal. And I'll reinforce this quite a bit, but those signals are a PTDR signal, pulse TDR. In some way, looks like a derivative, and that's really what's important when you're looking at it. TDR is a change in impedance moving forward. Next slide. So this is traditional TDR. Let's take the PCB3, and board 3, and we can rationalize in this case, really just like we did with the case of the frequency domain plots. That PCB3 is worse. I can see a bigger discontinuity, and PCB2 and PCB1, there's a little bit of discontinuities. But let's look at this in the context of data. I mean, the whole idea is let's turn what we can see here intuitively into a number. Going back down to the next slide. So I'm showing the TDR again in the top right plot. The bottom right plot is the pulse TDR. And as you can see, it does sort of look like a derivative in a way. And it sort of says, hey, this is the amount of impedance changes that we're seeing. And now we just have to tabulate it up. And that's where ERL comes in. How do you tabulate that lower right-hand curve? Because now I can ask all sorts of questions about what's more important. Is it what would be filtered out by an equalizer? And what the effect of filtering would have. It becomes much more obvious in the PTDR. So one thing to note is, remember, I said this is hypersensitive. These are reflections at a point. Well, guess what? All those reflections don't make it back to the receiver. And they're also in the transmission path, already included in the transmission path. So what we really are looking at is the reflection back at the transmitter, which, again, this turns out to be a very sensitive measurement. And the question then is, where do we set the limits? Moving down. Next slide. So this was the example that I used before. I'm sorry, this is sort of out of sequence, but it's still, we're measuring at a point. We're measuring board 3 test at a test point, and this is what we are measuring: pulse TDR and TDR right here. That's what those prior slides were. So this is just in reference for that. Moving forward, next slide. So how do you create a pulse TDR? And there's lots of ways that you could mathematically get to that point, but this is one way that I'm sort of suggesting. Using. Let's bring my other slides to synchronize to this. Okay, this is just a IFFT of a return loss. And I'm missing a subscript, that HR should be H sub R. And it's composed of an edge rate filter. Like when you do a TDR, people go, well, what's your rise time? Well, it's actually an edge rate filter. Rise times are equivalent to an edge rate filter. And then we apply a receiver filter because that's the context of that we're looking at. These things are used for a receiver, and receivers do have filters, they're not infinite bandwidth. And SII is the measured return loss, and X is a function representing a pulse in the frequency domain. It's basically the same. I didn't really go into that. I just wanted to show you that there is some math behind how to do this from an S parameter measurement. Nice thing about S parameter measurements is they can be calibrated fairly well to some sort of a point if required. Moving down to the next slide. So we can add up all the reflections, and I sort of was going to do all this. This is what we tried to do with originally for COM, and I went, well, you know, it gave you a reasonable answer, but it always seemed pessimistic to add up the worst of the worst of the worst of the worst. So let's look at the context again. And we do know that these are well-defined intervals. So at one point, you can only get so much reflection. And we'll talk a little bit about sampling phase and all of that a little bit later. But it's just the inverse of the baud rate, which is commonly called the UI. The result of this, sampling the PTDR, is going to be when we sample this, we end up with a sample PTDR, and that's what we actually operate on. We don't operate on the waveform itself. We start to use samples, and as you would do in a device, because devices are only sampled once per UI, typically. Moving forward, next slide. I think we talked a little bit about this in some of the earlier presentations. We talked about pulse convolution and noise and sampling. Once, your simulations normally have many samples per UI, a device only has one. So ERL is a statistical compilation of the red dots. So this is a this is a PTDR signal. The lower one is just for reference, the TDR signal, and that's of the board 3. And basically, we're going to look at the collection of N reflections of those N red dots. So, well, okay, I've got values and dots, and I can say, if I've got values and dots, now I just got to figure out what I want to do with those dots. Do I add them up? Do I statistically add them? And that's what I'm going to talk a little bit about in a minute. But we can gate it. I mean, because there could be a reason that we want to use gating, we might say, well, you know, that first section right there might be just in all my measurements. I don't want to look at that. That's going to pollute my measurements because it's a fixture or it's a coaxial connector. And I'm just going to look at the other dots. So the selection of which dots to use is basically a weighting gating function. I'll talk a little bit more about that later, why we do it, and that's under the advanced topic. I'm not going to go really detailed into that, but I'm going to go more details into what the parameters are that we use to create these dots, and then how to compute ERL. Next. So, statistically, these magenta dots, I probably should have used red, this is an old slide, but they represent a collection of reflections. And then I can combine those collection of reflections with a data stream, and the data stream will contain coding data, PAM or PAM2, PAM4, PAM6, PAM10, whatever you like. It's going to be in that context. So I can add them up as if those are a data stream of various different pulsars. And that creates, let's say, one of the curves of a probability density function in the middle. However, what we do is we look at all the points in between the points. So I sample one way or another way by some number of some degree of precision between each of the purple dots. And that creates a collection of probability density functions. This way we handle all the possible phases that could ever occur. And from that, we choose the probability density function that's got the largest variance. And then once we've done that, we've converted into a cumulative, this is a way of adding it up statistically, a cumulative distribution function that says, hey, if I look at an equivalent value of reflection at a particular BER or detector error ratio, what would that value be if it collapsed all to 1 point? And I included all of the sample phases here. And I just sort of says, well, this is kind of the worst one. Now moving down to the next slide.
Hey, Rich.
Yep.
Hey, Rich, before we move to the next slide, I don't know if Scott, you want to address this question. But we have a comment. It says R effective is presented as the multiplication of G loss, GRR, and PTDR.
And they are in time domain.
Yeah. Is it supposed to be a convolution of these terms?
No, multiplication.
All
It's
right.
a weighting gating function. It turns out receivers are terribly nonlinear, and the way we look at things is terribly nonlinear, time variant, and that's all this represents. Is ways that we think about problems in terms of reflections. It's just a logical way of looking at something. So moving forward, next slide. So there's a COM tool, a COM code tool, that is an example in IEEE that can be maybe used to compute COM. We have some standalone tools that we do this too. It basically takes an S4P file or a return loss S2P file, takes a COM spreadsheet, which has got all the parameters to compute ERL. You run it into this code, and then voila, pops out ERL. So moving forward, so the question now is, what are the parameters? Next slide. These are all the parameters that we use to compute ERL. And starting with the signaling rate. I'm going to go over each one of these, so hold your questions if you have any of them on this. Moving forward, next slide. So the first setup in that is the signal rate and the Gaussian transition time between 20 and 80%, and the receiver bandwidth, which is it's in terms of the signal rate, FB. So these are the units and values, and these are and there will be a keyword in COM associated with it that you'd use in a spreadsheet. FB would be maybe, it would be maybe 53 point something gigahertz or 58 gigahertz, and 20 to 80 would be in nanoseconds. So it might be 0.01, which would be nanoseconds, which would be 10 picoseconds, but you have to use in terms of, it's just a convention, happens to be what it is in terms of the standard speak. So we're just using the same values that are used in the standard because of it. The way it works in the standards, if folks don't know, it's if you use giga, thou shalt use nano everywhere. Anyhow, going forward. Next slide. So there's a bunch of other keywords. TFX is like a fixturing gating time, but it can be used for lots of other things. And maybe Scott will use this. And I'm going to show an example of what this really means. It's basically the text fixture delay divided by 2. So the delay is we're going to use this, but it's got a lot of other uses beside, and it's called TFX, and it's in seconds in terms of units. And there's another parameter here that if you have a package that happens to be in the COM table, you can cascade a channel with that, or basically a channel that's got no loss and no return loss with that to get the package. But you can cascade a channel with that. So let's say you built a host, okay, board for VSR or chip to chip, and you don't have your own package on it, but you know what your board is. So you put a reference package from the COM model on that. And it's just a logical parameter. 1 cascaded, 0 says no action. Moving forward.
Hey, Rich. Another question. Why not de-embed the fixture in the model instead of gating it?
Good question. The industry, you can do that, but the industry has got, in terms of the standards communities, have got very low confidence in de-embedding between various different companies and instrument manufacturers. And there's a lot of ways that you can get into trouble doing that. So it's a techno-political issue. It was put there for that. Right now, we have another way of doing this that we embed rather than de-embed. That's another methodology, using ERL rather than embedding. We de-embed, we embed. So that is the reason we don't do that, because, I mean, if you can guarantee to yourself that you can do a very, very good job, absolutely. But
I think the point here is that there are multiple de-embed methodologies, and coming up with a standard for that in a standards body, an IEEE standard body, with all the vested interests, it's a non-starter. It isn't going to happen. And so, yeah, you want to de-embed the fixture yourself and then pass it through ERL. It's a perfectly valid way of doing it.
There are standards that don't use its fixture. I mean, OIF, for example, does not use a fixture. It says, hey, if you mess up the de-embedding, hey, you just mess up the measurement. Rot's a rot. IEEE is not so. But in any case, there's a use for this TFX, so we can use it for a lot of different things. So it's a handle. It's just a parameter. Just consider it. I mean, we call it fixture delay. It's just a zeroing out delay. Let's call it that. I'm going to show that graphically in a minute. Next. Okay, so there's going to be a 2-key window, which is basically a raised cosine filter that just helps for the computational stability. It's a well-known cosine tapered window. Basically, it has very, very little effect unless your S parameters are not behaving particularly well. In other words, measurements typically have a noise floor, so it kind of gets rid of the effect of, if my measurements have got noise floors, then what do I do about it? Because I still can make a good measurement with an ERL. Anyhow, moving forward, next. Some other logical, and these, remember, these are just COM control parameters, TDR, ERL, ERL only, pretty much as they're sort of suggested, sort of enables the TDR, enables the TDR computation, the ERL computation, and when you're running the COM code, 0 enables the COM computation, 1 disables it. So in other words, if you only want to run ERL, you set ERL to only to 1 and the other values to 1 as well. Next slide. Okay, so N is the gating number. So this is, and these two numbers sort of go together. They're sort of like, the window as to where you want to look. You can call that a test fixture or whatever you want, but N is the span that we're going to look over. So in other words, if I reduce N, I'm only looking, let's say I reduce N to like 40 UI, and by N is in actually seconds, but let's say I reduce it. You wouldn't see there would be no computation between 40 and 100. There would only be between 0 and 40. So in this case, and I'm looking at this, it's just for this reference, it's got 4.1 dB ERL when I did the computation. So let's look at the next slide that includes a fixture delay. Well, if I put a value in there for TFX, what happens is those the red dots are all forced to 0. And then I only do computation from, let's say, 20 UI out. So now my ERL is 9.4. So, and you can use, and it's got a lot of uses. Between TFX and N, and adjusting that, you can hone in on particular reflections, which tend to be very useful. Next. Okay. So people have asked me this all the time. How do I determine TFX if I have a test fixture? And the simplest way that I know to do it is to basically take the finite impulse response, find the peak of that, use that as your delay, and then double that for the TFX number. Next. So let's look at small differences here. So let's say I've got a VIA that's 120 femtofarads. Let's model it that way. Let's say the HFSS and everything else is, yeah, it looks sort of like 120 femtofarads. I did it again, and it's like 20 femtofarads less. What difference does it make? So I may just want to just look at the ERL for tuning purposes, just for that value. So what I can do is I can adjust TFX, and I could have looked at the other VIA at 40, but I just happened to look at the one at, so about 20. And I can choose N, and my N goes up to about 25 here. So I'm only looking at that. So now I'm looking at the difference between, I can see the slight difference between 15.5 and 15.3 dB. Remember, lower is worse. Yeah. So moving forward, next. So this is the advanced topics, and this is one of the reasons we did it, is because we noticed that small packages always had worse return loss, but always performed somewhat better because we looked at we were considering very wide ranges of loss. In other words, let's say we have a 30 dB channel. On that channel, let's say 10 dB of that was package. So a short package might knock that 30 dB down to 20 dB end to end, but you can't see that, especially on a receiver. You can't see what the loss is. So how can we get at the loss and the reflection at the same time? And the idea was to compensate for the fact that with time, using time as a metric, we can adjust a weighting gating function. That was the question that somebody had asked prior with the G parameters. And then, of course, in that region, we can do an adjustment for DFE because we know that reflections that are close to one another are removed at the receiver with a DFE, sort of. And this is called compensable ISI. So here's the difference between compensable and uncompensable ISIs. We're going to put a number on this. We've gone round and round about this, and we decided that we're going to lock some things down, and I'll talk about that, just so that we can get good numbers for a specification. And both of these use NBX, which is the number, which is basically another value that's normally set to the number of DFE taps. And the thinking is NBX is going to be also linked to the highest loss in a package. Moving forward, next. So here's again these parameters. These are extra parameters, and these are required. And a lot of times we'll set NBX to 0, which makes the beta X and rho X parameters move. But we decided to lock these two parameters, beta X and rho X, down, 1 to 0 and 1 to rho X. Originally, I'm going to talk about that in a minute. It does make sense, but they both sort of do the same thing. By setting this to here, all we need to do is adjust the specification value for ERL. Otherwise, we have 3 parameters that all move in various different directions. So you end up in a specification chasing your tail by setting these parameters and figuring out the best values to set each one of these independently. So locking them down, you can get the same effect by changing the value of the ERL. Moving next slide. So this is that crazy equation. It's just basically a power equation, a loss equation. And basically it's related to the amount of loss beta X that you'd see in a package. And this is the equation that we use for beta X. We can find beta X by asking ourselves what the maximum loss is in the system and saying what is the differential loss between short and long packages, and come up with a factor for that and make that beta X. But if you make beta X 0, notice G loss goes to 1. So we decided that that's, originally we actually thought we were doing a good job, and things correlate very well, but yet when you go to set a value for a standard for what ERL should be, it starts to become very difficult to do this between various different standards. So to be consistent across the industry, it was, although there was good intentions as to utilize this, we just set it to 1. Next slide. And all reflections are not equal. And I'm going to go over a little bit of this. And this is probably the most important thing. This is more important than the loss. I think the shape of this GRR and the prior value, the prior G loss, are very, very similar. They're similar enough that we can just use that, only one of them as a gating function, because they both apply over the same NB range, which would be NBX actually. So the goal is to adjust the return loss to accommodate for the DFE, which may remove some of these reflections. You may think it's going to move more, and I'll show you why it doesn't in a minute. But this is actually the first term of a scattering function, which again sounds like a great idea, except for you end up with a chase your tail in terms of finding out what rho X needs to be, what beta X needs to be. So we just set this guy up to 0.68, which makes that rho X times 1 plus rho X 1. Moving forward. So there's some caveats here. Is that NBX is, again, normally used to adjust the PTDR waveform, and you'll see, I think I'm going to graphically show that in a minute. It's not appropriate for all topologies because you don't. A lot of topologies don't have a DFE, and a lot of them, the effect of the DFE is not comprehended in the test point. So in other words, wherever you measure the test point, even if you have a DFE there, it's not going to do anything for the return loss that you're measuring at that point. So it's totally out of context. There are some cases, like for a cable assembly, you may want to just say with a fixture on it, a test fixture on it, it's just not appropriate for using MBX there. So the latest standard set the rho x value to 0.618. Locking down these two values simplified the whole process and reduces the number of moving parts so that we can create a good specification. Moving forward, next slide. So this is a graphical view of maybe a pulse response, okay? And there are reflections on this. And the red dots represents a DFE. This is at a receiver. Pretty much this, what we saw very similar to what we had done in the prior examples, but this is the pulse response. Notice the red dots, and by the way, the green dot at the top is basically the signal, and you basically can subtract all of it, statistically using convolution, subtract all of the dots from the main cursor dot to figure out what the eye height would be, but you're not going to include the red dots. Ooh, that's interesting. So that seems really simple. We just remove them all in the PTDR. Well, that's saying that there's no effect for those red dots, for the reflections that the DFE takes out. But the DFE doesn't take them out of the channel. You know, it only takes them out of a point in time in the receiver. And this is what the weighting gating function does. It says, well, how much of those we really want to take out? Next slide. So if I look at those other squiggles, and I set up the experiment, so I just see those other signals that I just see the other signals that then that is the effect of those reflections in that DFE range. So even though I may have removed them, I'm getting effects from the DFE, even though it's not in the DFE range. And what is it? It's going to be some proportion of those reflections, but it's not going to be reflections that are that deterministic. I can bound them, and that's one of the whole purposes of the gating regions is, well, how much do I want to bond? How much am I going to really bond by? And one thing to notice is, look at the size of those reflections compared to the main cursor. They're way down, so the effect is much smaller. So I just want to remove some of the effect of the big effects of the TDR, of the pulse response in the DFE range, in the reach of the DFE. I just want to remove some of that. I don't want to remove it all because there are effects from that. And moving forward, the next slide. So this is what the gating from the previous slide, the R effective is, and this is of T, the R effective, which is what we're going to use, is G loss times GRR times the pulse. And now we're going to look at a simple example for this. So this is like pretty much the last slide, very close to it. But so I'm going to spend a little bit of time on that. My reference PCB looks like the red, okay? And the end of the on the left-hand side, the dot is the end of the fixture, which we sort of removed. It's already been removed. So we're looking at from where the black dot is to the right. Okay. So if I look at this, and let's consider this a package, looking back into a package. TFX is to the red dot, but NBX is a range. And if you can see the magenta line, that's what the weighting gating function looks like. And the fact that this is what it sort of needs to look like to be able to comprehend both the loss and the reflection. So what happens is when I multiply in time the magenta times the red, I end up with the darker red. Or maybe it's a black there. It looks like a black, I guess the black function. And that's the effect of the weighted gated PTDR. Notice what happens. The ERL goes up. It gets better with NBX21. So the weighting gating function, and you can use all of these parameters to adjust and determine what the effect is in a particular one design over another design just by changing TFX, NBX, and N. And NBX most likely is 0 for a lot of physical analysis, but in a package analysis is not. It's whatever your equalization range is. Next. So in summary, ERL is a scalar number that represents return loss for a particular data rate and a required BER or DER and a certain type of signaling, NRZ, PAM4, and PAM6. It will adjust to the signaling. It basically tells how many levels of amplitude modulation you're doing, and it'll adjust ERL accordingly. And it may take account for package loss and the DFA. Doesn't always have to do that. And it's computed from a single pulse TDR. And again, the thing to remember is from a diagnostic perspective, it looks like the derivative of the TDR. In other words, if you took a TDR, shifted it in time and subtracted, you would get a pulse TDR. ERL is normally specified in many standards above 50 gigabits because it gives you a particular scalar value that we can set a limit for. And we can tune designs for using the parameters in ERL by adjusting them. But you can tune features of a design, which is more or less a segue into what Scott is going to be doing in the next part of this presentation, which is in a few weeks or so. And I think next slide is a thank you.
Yeah, so Rich, I thank you for this. And so you gave me a good segue into, so Rich has gone through the technical details of ERL, how it is used within the standards body. So if, so some of you are probably like me and your eyes are glazed over. Because there's an awful lot of math, there's an awful lot of analytics in here, and it takes a while to kind of grok this and understand what's going on. So y'all know me as an experiential engineer. So I took what Rich has done and what we have done to place this in a simplified tool framework that we built up at Samtec. And I'm going to show you how to use it like a black box. It's just a magic box. And the beauty of ERL is that it gives you one number. And I treat that number as a relative number. That is, I can use it to determine the relative goodness of one design versus another. So what I'm going to do in 2 weeks is we're going to go through a couple of design cases for design of launches for connectors, where we go through the different options in a design of experiments kind of setting and show just how valuable this is. And I'll also show the effects, the various effects of different lengths of DFE in terms of how it basically cleans up the channel and allows us to use things that are that, according to return loss curves, might not have been good enough to work before in the past. Any other things that you'd like to talk about, Rich?
Nope. Not really. Any other questions?
All right. Well, thanks.
Get it done in less than an hour.
Yeah, we actually.
He looked at it and says, "You can't do that." It's tricky.
Any other questions? Well, we have no other questions. So, Matt, you want to?
Yeah, definitely. Rich, I also want to give you kudos for not having a internet disconnection. So, that's another gold star in your book today. So we appreciate that. Scott, Rich, as always, thanks so much for the support for Geek Speak. We want to thank all of our listeners for joining in at another webinar. As always, if any of the listeners have questions for the Geek Speak team, please feel free to contact us at geekspeak@samtech.com for any technical SI related questions. Please feel free to contact our signal integrity leaders, including Rich and Scott at sig@samtech.com. This recording and all recordings for Geek Speak are available on demand at samtech.com @samtech.com/geekspeak. We also post a PDF version of the presentation there as well for your use. So again, representing Rich and Scott, we thank everybody again, and we'll look forward to seeing everybody in 2 weeks. Everybody have a great day.